In the last lecture, we saw and understood the time shifting operation on discrete time signals, and now in this lecture we will understand the next operation on discrete time signals, and the operation is time scaling operation. To understand the time scaling operation on discrete time signals, let's take one discrete time signal xn, and after performing the time scaling operation, we will have a new discrete time signal which is, let's say, yn. Then yn will be same as the initial signal xn with one change. Initial signal is xn and the change will be there in place of n. Instead of n, we will have an. So here we are performing the time scaling by a. We are scaling the time by a. Now depending on the value of a, we will have three types of time scaling, and the first type is known as time compression, and time compression is also known as decimation. It is also known as decimation, and not only decimation, but it is also known as downsampling. Now let's see for what condition on a we will have the time compression as the time scaling. Whenever mod of a is greater than 1, we will have time compression as the type of time scaling. I will give you few examples in which mod of a is greater than 1. When a is equal to 2, it is obvious that mod of a will be equal to 2 and 2 is greater than 1. So when a is equal to 2, this condition is satisfied and we will have time compression. This means if we have a discrete time signal xn and we perform the time scaling, and after performing the time scaling, if we have x 2n in place of a, we will have 2, then this particular signal will be compressed form of this signal. The waveform of this signal and this signal, when you compare, you will find this signal is having the waveform which is compressed as compared to this signal. Similarly, when we have a equal to -2, again you will find mod of a is equal to 2. So this condition is satisfied. Similarly, you can think about the other cases. Now we will move on to the second type of time scaling, which is time expansion. Time expansion is also known as interpolation. It is also known as interpolation, and not only interpolation, it is also known as upsampling. Time compression is known as downsampling and time expansion is known as upsampling. And we will have time expansion as the type of time scaling when mod of a is less than 1. I will give you few examples. When a is equal to 1 by 2, or you can say 0.5, you will find mod of a is equal to 0.5, which is less than 1. So in this case, we will have time expansion. So if there is a discrete time signal xn, and if we perform the time scaling with a equal to 1 by 2, we will get a new signal xn by 2. And when you compare the waveform of this signal and this signal, you will find the waveform of this signal is expanded as compared to this signal. Therefore, this particular case is known as time expansion. You can have one more example. A is equal to -0.5 will give you mod a equal to 0.5, which is less than 1. So this is one more example of time expansion. Similarly, you can think of other cases. Now let's move on to the third type, which is time reversal. Time reversal is the special case of time scaling, and time reversal will be there when a is equal to -1. So xn, after performing the time reversal, we will have x minus n. So you can see that to get x minus n from xn, we simply need to flip the waveform of xn about the y-axis. Now we will take one example to understand time reversal in a better way. Let's say signal xn is equal to 1, 2, 4, 5 with 2 as the value of xn when n is equal to 0. Now when you perform the time reversal and have a new signal x minus n, then the whole waveform will flip about the y-axis. This means the whole waveform will flip about the y-axis and equal to 0, and therefore we will have 2 when n is equal to 0. There will be no change here, but this 4 will come at place of 1, and this 5 will come one place behind 1, and this 1 will go in place of 4. So this is what we have after performing the time reversal operation on xn, and now we will understand time compression operation by the help of one example. And in this example, the discrete time signal xn is equal to 5, 3, 7, 8, minus 2, 4 and 9, and 8 is the value of xn when n is equal to 0. And we will perform the time scaling operation, which is the case of time compression, because the signal we are getting after performing the time scaling is equal to x to n. So you can see that we have 2 in place of a, and therefore mod of a or mod of 2 will be greater than 1. Therefore this is the case of time compression. We know xn, it is given in the example, and we need to find out x to n. For this we will focus on different values of n. When n is equal to 0, x to n will be equal to x0. And from here you can see that when n is equal to 0, xn is equal to 8. This means x0 is equal to 8. So x to n when n is equal to 0 is equal to 8. Very simple. Similarly, we will calculate x to n when n is equal to 1. This will give us x2, and x2 from here is equal to 4. Therefore x to n when n is equal to 1 is equal to 4. Now let's calculate x to n when n is equal to 2. We will have x4, and from here it is clear that x4 is equal to 0. Why? Because 9 is the value of xn when n is equal to 3, and after 9 we have zeros. Therefore when n is equal to 4, we will have xn equal to 0. Similarly, if you go on calculating the values of x to n for the values of n greater than 2, you will get zeros. Therefore I will stop here, and now I will focus on the values of n which are negative. When n is equal to minus 1, we will get x minus 2, and from here we can see that x minus 2 is equal to 3. Now I will put n equal to minus 2. This will give us x minus 4, and x minus 4 is equal to 0, because 5 is the value of xn when n is equal to minus 3. For minus 4, for minus 5, all the way to minus infinity, xn is equal to 0. Therefore when you calculate x to n for the values of n which are less than minus 2 or equal to minus 2, you will get 0. So I will stop here, and now I will try to construct signal x to n. Signal x to n. You can see that when n is equal to 0, we have 8. When n is equal to 1, we have 4. So after 8, we will write 4. When n is equal to 2, we have 0. We will not write 0. And when n is equal to minus 1, we have 3. We will write 3 here. When n is equal to minus 2, we have 0. We will not write 0. So finally, we can say that x2n is equal to 3, 8, 4. This is the answer, and 8 is present at n equal to 0. Now we will solve one more case of time compression. We have the same xn signal and we are performing the time scaling operation, and this time we are getting signal x3n. So again you can see that mod of a is greater than 1, therefore we have the case of time compression, and we will try to write down x3n directly after analyzing this case. In this case, we performed the time scaling and we got a signal x2n. x2n, after performing the calculations, we got equal to 3, 8, 4, where 8 is the value of x2n present at n equal to 0. Now if you focus on xn, you will find xn is equal to 8 when n is equal to 0. Therefore, 8 is the value of xn when n is equal to 0. Similarly, 4 is the value of xn when n is equal to 2. 3 is the value of xn when n is equal to minus 2. From this analysis, it is clear that we have chosen only those values of xn for which the corresponding value of n is a multiple of 2. We are having 2 here, therefore we will choose only those values of xn for which the corresponding value of n is a multiple of 2. Therefore we have 3, 8, 4, 0, 0, 0, 0, 0, 0. Now we will focus on x3n. In place of 2, we have 3. Therefore we will choose only those values of xn for which the corresponding value of n is a multiple of 3. 8 will be there. 8 will be there. I will directly write down x3n. 8 will be there, present at n equal to 0. Then we will reject minus 2 because this is present at n equal to 1 and 1 is not an integer multiple of 3. We will reject 4 as well because it is present at n equal to 2, but we will accept 9 because it is present at n equal to 3. So we have 8, then 9. After this we have zeros, and if you consider few zeros after 9, then we will not accept this 0, but we will accept this 0 because this 0 is present at n equal to 4, this 0 is present at n equal to 5, and this 0 is present at n equal to 6, and 6 is a multiple of 3. Therefore we will accept this 0. Similarly, you need to follow the same process, and now we will focus on the values of xn which are for the negative values of n. 7 is present when n is equal to minus 1. We will neglect this. 3 is present when n is equal to minus 2. Again we will neglect this, but 5 is present when n is equal to minus 3, which is an integer multiple of 3. Therefore we will accept 5. So finally we have obtained x3n equal to 5, 8, 9. So in this way you can directly write down the result after performing the time scaling when the case is time compression of the signal. Now we will move on to the next example, and using the next example we will understand the case of time expansion. So let's quickly write down the signal in this case. The signal in this case is yn, and yn is equal to 4, 3, 5, and yn is equal to 3 when n is equal to 0. So we will put arrow mark below 3. Now we are interested in performing the time scaling, and after performing the time scaling operation, we got a new signal which is yn divided by 2. So here in this case you can see a is equal to 1 by 2, therefore mod of a is less than 1. So this case is the case of time expansion. Now let's quickly move on to the calculation part. We will put n equal to 0 like we have done here, and for this we will calculate yn by 2. When n is equal to 0, yn by 2 is equal to y0, and y0 means value of yn when n is equal to 0 is equal to 3. So y0 will be equal to 3. This means yn by 2 when n is equal to 0 is equal to 3. Similarly, we will put n equal to 1. This will give us y1 by 2. And you can see that there is no corresponding value of yn for n equal to 1 by 2. Because n cannot be 1 by 2. N is an integer and it cannot be 1 by 2 or 0.5. So 100% we are going to get 0. Now let's put n equal to 2. This will give us y2 by 2, or simply we can write y1. y1 means yn when n is equal to 1. We will have 5. Now go on performing the calculation and you will get 0. Let's put n equal to -1. This will give y minus 1 by 2. Again we will have 0 because fractional values are not allowed for n. N equal to -2 will give us y minus 1. Now this time we will have 4 because 4 is the value of yn when n is equal to -1. So y minus 1 is equal to 4. Now put different negative values of n which are less than -2 and you will get zeros. So we will stop here and now we will try to get our signal yn by 2. First we will start with the value which is present at n equal to 0, which is 3. So we will have 3 here, and then when n is equal to 1 we are getting 0, so we will put 0 here. After this, when n is equal to 2 we are getting 5. Then we have zeros, so we will stop here. When n is equal to -1 we are getting 0, so we will put 0 here. When n is equal to -2 we are getting 4, and after this we have zeros. So finally we are getting yn by 2 equal to 40305. Now compare this signal and this signal. You will find here we have 435 3 terms, here we have 40305 more terms as compared to this one. Therefore there is expansion of the signal, and therefore we call this case time expansion. Now let's quickly move on to the next case, and in this case I will give you the shortcut method. Again we are performing the time scaling, and the time scaling is the case of time expansion. We are having yn by 3 as the new signal. Now to write down yn by 3 directly, we will analyze this case. Here you can see that we have yn by 2. 2 is here. So take this 2, subtract 1, you will get 1. So 1 means 1 0 between the numbers you are having. So put 1 0 here, put 1 0 here, you will get 40305. Now in this case we have yn by 3. Take this 3, subtract 1 like you have done here, you will get 2. 2 means 2 zeros. 1 means 1 0, 2 means 2 zeros. Therefore put 2 zeros between the numbers you are having. So you have 4003. I will write down the answer directly. You have 4, 2 zeros, then you will have 3, and again you need to put 2 zeros between 3 and 5. So 0, 0, 5, and don't forget to put the arrow mark in both the cases. So this is the answer. This is y n by 3. In the coming lectures, we will solve many questions based on the operations, and there we will use these shortcut methods. So this is all for this lecture. We have seen how to perform the time compression, how to perform the time expansion, and how to perform the time reversal. So I will end this lecture here. See you in the next one.